maybe I will try to use my XP pen here. XP pen. Anything, just please stop me if you need to additional some explanation. All right. So discussion today on still on homomorphism theorems and ring of fractions. It is a first part. The second part is vector spaces. Vector spaces. I hope I can start our discussion on vector spaces today. Then I will continue after the day after tomorrow. Okay, so homomorphism theorems first. Last time we discussed quotient rings. Quotient rings and the homomorphism theorems, they are almost the same in group's case, but there are some differences. So I want just give your attention, just bring your attention to that differences between group quotient groups and quotient rings. So what we have? So last time we had a R as a ring, and its ideal I. This ideal I is ideal subgroup, right? Subgroup with respect to addition operation in R. In this R. So that's why cosets also with respect to addition. So we have cosets. This is set of cosets which are given as a plus I. I is ideal. I is an ideal. Then A runs R. So these cosets with respect to addition operation in R. But in R we have one more operation, multiplication. So we will try to introduce a multiplication operation in R over I in that quotient group because I is being subgroup of an abelian group. We don't care that I is a normal subgroup, so that's why R over I always exists. This is a quotient group. So we introduced as follows: A bar times B bar is A times B, or let me write AI times BI that we have defined as A times B plus I. Okay, now we should show that this product doesn't depend on choice of these representatives A and B. So that means I will take another A as A prime here, and the B prime here. They are the same. Then product of these two is A prime plus I times B prime plus I in fact, by definition, this is A prime times B prime plus I. Since left-hand side, the same, they are the same. Products must be also the same. So that means these two must be equal. These two cosets must be equal. What does it mean? This is equivalent to say this difference AB minus A prime B prime is an element of I, having that A minus A prime, provided that A minus A prime is in I, and B minus B prime also in I. So that gives us well-definedness. How to prove it? Just easy. Just take AB minus A prime B prime. Write it as follows: A B minus A prime B prime. Add to this, say A prime B, and subtract A prime B. Now regroup now. By regroup, then what we have is a result. Sorry. I will group these two, and these two. So I will get A minus A prime, or let me write A minus A prime times B. Then from that I will let me write this a plus. Plus from that I will factor out A prime from that too. So I will get B minus B prime. Since I have these two properties, so this guy is element of I. This also is an element of I. Since I is an ideal, and is ideal, right? So any element of I times an element of ring R, this product will be in I. So the same for second one. So result, this guy is in I. So that means we have this difference in I. So that means product operation in R over I is well defined. Okay. Next one. Next is why is this important? Quotient ring. This time. Why this important? This is interesting ring. From original ring R to this ring, we have surjective homomorphism as the in groups case. But that one is homomorphism of rings.
Isamiddin aka, rабочий stolingiz chiqdi ekranda.
Hozir. Bir sekund. This one is problem of it is a problem of online teaching sometimes. Okay. Now, can you see now?
Yes.
Okay, thank you. So, second thing, which one I want to say is the following. I have R, then homomorphism from R to R over I, for any ideal I. This is a surjective homo because this is a ring. This is also is a ring according to that we introduced just now. By the way, that two axioms, distributivity of multiplication with respect to addition operation, can be easily checked. No problem. I hope you can do it. So I don't want to do it because it is similar to that in group's case. I just checking that the axioms easy. Okay. So now what this homomorphism? This homomorphism sometimes denotes a pi, is called projection homomorphism. This homomorphism does this take A, then assign to this A its class A bar. So this is homomorphism easy to see because if you add A to B, you will get A plus B. Then, according to the definition of addition operation in this quotient ring, you can write it as A bar plus B bar, and it is the additivity and the multiplicative also. Just now, according to this definition, just now we introduced. So we have homomorphism, such a surjective homomorphism. Okay, now what we have, if we have number 3, which one I want to discuss is, if I have homomorphism F from R1 to R2, and take as a I, the kernel of this homomorphism. Then, of course, I can consider quotient ring with respect to this. So I will get here quotient ring R1 over I. Then there is a projection homomorphism, surjective onto homomorphism from R1 to R1I. Then there exists unique homomorphism from this quotient ring to R2. H. There exists such a homomorphism H from this quotient ring to R2, such that this is a F, this is a pi, then F is written as H composition pi. Any such homomorphism from R1 to R2 can be written as a composite of these two homomorphisms. There exists unique such a homomorphism H. Now H you can define as follows. H of A bar is given as a F of A. Easy to see this is homomorphism, ring homomorphism. Then you can check this property. So F is written as a H O pi. Okay. Now let us go to homomorphism theorems now. Homomorphism theorems. The first homomorphism theorem. If you have homomorphism F from ring R into R prime, then this one is the image of homomorphism FR. If it is onto, then this is an ideal of R prime. In general, it is not ideal. It is not ideal. It is just subring if it is not onto. In general, it's not ideal. It should be onto here, sorry. So if you have any homomorphisms from R to R prime, then the image of R is subring. You have, so subring means you have a ring again. So this is a ring. You have two rings. One is R over kernel of F. Another one is F of R. Then this theorem says these two rings are isomorphic. So that means there is a isomorphism. Isomorphism, you can write it as follows, as already done it. Let me denote as a phi. Phi of A bar is F of A. So this is isomorphic to this. Phi is isomorphism. It's isomorphism. Need to check. In group sketch, we already done it, so it is easy to verify. Again, this is a homomorphism, but this time you should check it for two operations: addition and the multiplication operations. Okay, correspondence theorem. Correspondence theorem. Let me correct this. This is just subring. Subring. A subring of R prime. If it is onto, homomorphism is onto, then it is ideal. If it is just into, then it is not ideal. It is just subring. Here you can see onto case. If you have homomorphism from R to R prime, which is onto, then what we have? If you have an ideal in R, then its image in R prime will be again ideal of R prime. So this theorem says, correspondence theorem says, if you have two set of ideals, one is family of ideals in R, you can denote this as R right here. you can denote this as F. What is that? This is those ideals. These ideals of R such that kernel of F is in I. Another one is S, just all ideals. Let S be the set of all ideals, the family of all ideals. Ideals of R prime. Then between these two sets, there is a one-to-one correspondence. How this correspondence can be established? Again, you will take. Let me take psi of from S F to S as follows. You will take psi of I as a F of I. Since this is onto, please pay attention to this. This is onto. When it is onto, the image of any ideal is an ideal, in another ring, R prime. So that inverse from this to this, from S to SF, is given as follows. It is, let me write here, psi minus 1 of the inverse of J, which is F minus 1 of J. Please pay attention here. This set theoretical pre-image here. This is the inverse of psi. So that means psi or psi minus 1 is identity. And then the same psi minus 1 and or psi. This psi and psi minus 1, they are inverse to each other with respect to this composition position. Here is the just set theoretical pre-image of the ideal I, ideal J. It is ideal containing the kernel. Why? Because this ideal contains 0. I is a pre-image of 0. I is a pre-image of 0. Since any ideal contains 0, so that's why its pre-image also contains a pre-image of 0. So the pre-image of J contains pre-image of 0, which is I. So these two functions are well defined. Their composite is just by identity function, just can be checked. So this is a correspondence theorem. Okay. All right. Next is unfortunately, if I comment on it hangs. Sorry. Yeah. I have to wait the update. Okay, sorry. Okay, so I have to less comment. Okay, let me call next theorem. Again, if a homomorphism of R onto R prime again, see, onto, and I be an ideal of R containing this, and we have two such kind projections, G and G prime, natural projections, natural homomorphisms. I'd like to comment. Okay, I have R. Let me do it. R. Here I have I, right? Here I have R prime and F I. Fi. Since it is onto, so this is an ideal of R prime. I have two projections from R and from R prime. I have projections. So this is F, my F. I have two projection maps here. One of them is denoted by G. This is denoted by G prime. Then result I got this quotient ring and another quotient ring. So these two quotient rings are isomorphic. There exists unique isomorphism between these two quotient rings. R over I and R prime over Fi, such that this diagram is commutative. So that means if you start from here, go by using F to R prime, from R prime to come here, or first apply projection rule, then go to the right by using H, the same, so which is given here. First you apply F, go here, then by applying J prime, you will go down. Then another way is first you apply G, projection homomorphism, then apply to that this isomorphism H, then you will get the same element here. So that is given by this equality. So what is the H? Again, H of A bar, let me write H of A bar is given as F of A bar, definitely. H of A bar, this bar with respect to this ideal. This bar with respect to this ideal. So for each this coset, you will assign FA coset, but coset is given by this ideal Fi. So this is a homomorphism. You can easy to see this is one-to-one correspondence and preserve that two operations, addition, multiplication operation in these two rings, quotient rings. Okay. Corollary from this theorem. Corollary. If you have I1 and I2, two ideals of R, Then of course you can make the following things. You can form first this quotient ring R. Let me write that as follows. I will take R. Here I have R over I2. I have such a projection homomorphism. From this I have projection homomorphism to R I1. But here again I have this guy. So that means since the I2 contains I1, so I can consider quotient ring again I2 with respect to I1. So I have the following. From here I will consider the following. R, let me denote this R bar here. R bar, so R bar over I2 bar. So what I have? From apply this theorem. Yeah, sorry. Let me be correct here. This I will take with respect to I1. This is with respect to I2. Then exactly will be that case which in my theorem. And again, so roughly speaking, you will take R, then projection rule, projection homomorphism R over I1. If you denote it the R bar, then from R to I2, then from here you have projection rule here. So then in that case, R over I2, which is this here, is isomorphic according to this, is isomorphic to this R over I1, which is this R bar, over I2 over I1, which is given here as a I2 bar. So exactly just from this, choosing which one R and which one R prime, you can easily see this homomorphism, this isomorphism, sorry. Okay, so I have, all right, so let me write here 1. Yeah, 1 here, 2 here, here also must be 1. Also must be 1. Okay, next one is system is hanging. So next theorem, okay, let's look at next theorem. If you have two ideals, I and J of the ring R, then you can take the intersection. So intersection in I, definitely, it will be ideal in I. Then you can define the sum of these two because they are groups with respect to addition. So that's why you can just take summation of these two ideals, I and J, because with respect to addition operation. So you will get again ring here. So that ring you can take quotient ring with respect to J. So this theorem says you have this quotient ring and this quotient ring. So they are isomorphic. In groups case, we already considered this. Nothing different from groups case. Only difference is just checking this isomorphism to be a multiplicative. Also can be easily checked in from groups case. You can easily obtain this isomorphism. Definition is the same. This isomorphism. You can take element of I sent to this, then with kernel of that homomorphism will be I intersection J. So from first homomorphism theorem, you will get such a isomorphism. Okay, now so now let that any questions, please, related to homomorphism theorems? If no questions, I want to discuss this theorem now. If you have some integral domain R, then you can embed this integral domain in a field. So that means part of elements of R you can invert, all non-zero elements of R you can invert and then form as a field. Then this R can be included that field. So this is a construction of that inclusion. It's called the embedding of R into a field. What we will do? We will take this Cartesian product R and R without zero. Then define on this S relation, binary relation tilde as follows. I will take two elements A, B, and C, D. I call them to be related if and only if A times D equals B times C. So ADE. If AD is BC, I will call that two pairs AB and CD to be related to each other. This relation tilde is an equivalent relation on S. It's an equivalent relation. Why? Because any AB is equivalent to itself. Why? Because in that case you have AB, here also AB. So A times B equals B times A. So you will get AB is AB. In that case, nothing to do. It is symmetric because if AB is related to CD, so that means if you have this, you can just change BC equals AD, then you will get CD is related to AB. So that means your symmetricity. The reflexivity is given, transitivity is given as follows. Let AB related to CD, and the CD stand related to EF. So this related to this means AD times BC equals. This related to this means CF times DE. CF equals DE. Then what we will do? Just multiply this part by F. Once you multiply this, then this part you can multiply by B. So this equality multiplied by F, this equality you can multiply by B. They are non-zero here, non-zero. So now you can see BCF, BCF you get. So that means ADF is BDE. ADF is BDE. Yeah, you can now cancel out this D. So you will get AF is BE. So that means AB is related to EF. If AB related to CD. In the CD, it's term related to EF. Then AB is related to EF. So that is a transitivity. Now, since this is an equivalent relation, you can consider equivalent classes. Equivalent classes, the equivalent classes of this relation, they are denoted by A over B with a representative AB. So the representative, the class containing AB, we denote A over B. So that classes, that set of that classes, we denote by F. So now you have some set of equivalent classes. On this set of equivalent classes, you can define operation, addition and multiplication operation. Addition operation we define as follows. So we have one class plus another class. So adding these two classes means one more class. First element of that class, representative of that class, is AD plus BC. Second element is BD. Multiplication is defined as follows. So the first element of the representative is AC. Second element is BD. So this addition, this multiplication on F. With respect to these two operations, F is a field. So what is it? First of all, it is a commutative ring, because any integral domain is commutative. So that is addition multiplication operation is commutative. These two operations are well defined. How to prove it? You can take another other representatives for AB, one representative of this class AB, another class A prime B prime. Let's say AB equals A prime B prime, CD equals C prime D prime, which is given here. Then adding up and multiplying them, you should get classes which are the same with the right hand side. So what does it mean? This means AB prime equals BA prime. This means CD prime is DC prime. Then if you multiply these two, if you multiply this by DD prime, this you multiply DD prime, so you will get this equality. This you multiply BB prime, you will get this equality. Now you can add up this. Once you do it, then you will get this and this. So you can factor out from this side the B prime D prime. So you are left with AD plus BC, B prime D prime, and the BD, A prime D prime plus B prime C prime. It is exactly this says. Then this addition, A prime over B prime plus C prime plus D primes, adding, you will get the same with this, because they are equivalent. So you have here A prime D prime plus B prime C prime over BD B prime D prime. We need to show representatives AD plus BC comma BD is related to A prime D prime plus B prime C prime comma B prime D prime. So that means this multiplying this must be equal this multiplied by this. What is given here exactly? So that's why this class, the same with this class. That means addition operation is well defined. The same for multiplication operation. Exactly this way you can prove that the multiplication operation also is well defined. Here is given that which I just now spoke. Okay, then addition and multiplication is given, 0 is given, additive identity is 0 over B class. Multiplicative identity also is given, it is B over B class. B over B class. B is not 0. Then if you have AB, then the additive inverse of AB is minus A over B, or A times minus B. Doesn't matter. Okay. Then multiplicative inverse B over A is A over B, or the multiplicative inverse A over B is B over A, because B is not 0. If this element is not 0, means A is not 0. 0 is given this way. So that's why this is not 0, means A is not 0. Once A is not 0, as a second part of that pair, you can take A. So B over A. If you multiply these two, result will be multiplicative identity. So thus, F is a field. Now, that ring R has its copy in F. Copy consists of A over 1 form classes, A over 1. For each A, you can assign A over 1. So this function is one-to-one function. Why? Because if A equals B, then A times 1 is B times 1. So that means A over 1 is B over 1. If and only if this image of them are the same. This is a one-to-oneness of F. One-to-one function. Then moreover, this is not only one-to-one. This is homomorphism. Adding up to A and B, you will get, according to this, A plus B over 1. So this is given A times 1. This is given 1 times B. This is 1 times B. 1 times 1. Then it can be written as A over 1 plus B over 1. Or this is the image of A. This is the image of B. And the same for the product. A by AB over 1, the image of this. Then you can write this way. By definition, it is A over 1 times B over A, B over 1. So A over 1 is the image of A, and the B over 1 is the image of B. So this is homomorphism. One-to-one homomorphism. So that means R and R prime you can identify. So R prime is exact copy of R in F. So R and R prime, they are isomorphic. Now what it will give us? So that means this R is embedded in F. Inside of F, we have copy of R. Now, let me just go to introduce case. So as a R, a bit notations are different. Okay, let me explain here. Let us take as a Z R. Then as a F, you will get rational numbers. So Z is included in rational because not Z. R prime is a copy of Z in rational numbers. But for copy, we have copy is equivalent classes. So that's why for copy, we have the following rule. they are being classes, they are they satisfy the following condition. No, I mean they are equivalent according to this equivalent relation. A over B. So that means all elements of A over B are elements of the following form. You can write this A over B. Let me write it. What's A over B? A over B in fact it's given here. A over B is CD with this condition, CD from R cross R star means non-zero elements, such that A times D equals B times C. If you denote this as a K, you will get this result. A times B equals K times C over K times D. A times K times EB, huh? K times correct it. It's not K. How to express this equality in other terms? That means if you multiply this way must be the same. So that's why multiplying by K, nothing is changed. So that is why in rational numbers we can multiply numerator and the denominator by K, because any rational number, it is not a number. They are classes. Rational numbers are classes. So that's why we can take one A over B or any element of that class, say 1 over 2, 2 over 4, 3 over 6, or 2 over 3, or 4 over 6, etc. For each class, we can take infinitely many represent, because representatives many. Any representative will can be taken to present that A over B. So that's why in rational numbers we can just cancel by K. That was my intention to explain. Last time I promised why we can just cancel by any K in rational numbers. Okay? Any questions, please? If no questions, let me, this is the final comments on rings. Let me now go to another topic, which is vector spaces. Vector space, today's discussion. What is vector space? For the vector space, you have the following two functions. Let us express it in terms of functions. So we have F, we have non-empty set V, we have V cross V into V. One function. we have scalars. Scalars, set of scalars, let me denote as a F. This is a field. So we have another function G from F cross V into V. Again, to simplify writing, this we will denote as a plus. This we will call multiplication by scalar, not product of two elements from V, but scalar times an element of V. With respect to addition, V must be abelian group again. So that means this function must be given. This is the first axiom. This axiom, this addition must be commutative. Commutativity must be associative. Must exist zero element with respect to this F. With respect to this F, must have inverse. This time, this inverse we denote the minus U as in Ring's case. So the existence of additive inverse. So first axiom is called closure and addition. Second one is commutativity of the addition, associativity, property of addition, existence of identity, additive identity, and existence of additive inverse. 5 axioms. These 5 axioms says your V with respect to addition must be a group. Abelian group. Must be an abelian group. This is the first part of the axioms. Another part. Now, into relation, there are 2 operations now. Number 6, closure under scalar multiplication. That means that function G must be given. It is denoted C times U. C times U. For any element of V and for element of F. Here C from F U G. Then next one is distributivity. Distributivity of that scalar multiplication and addition. Cu plus Cv. Cu plus V must be Cu plus Cv. And here another distributivity property. C plus D times U is Cu plus E. Please pay attention. Here this addition is given in V. This addition also in V. But this addition is given in F. This addition is in V. Okay, then here, next axiom, associativity property. This multiplication is given by G. Result is an element of V. So this also is given by G. See, these products are given by G. But here, this product is given in F. But this product is given in G by using G. So you see, interrelation giving that product in F and the product which we defined just now in V. Here, 1 times U is U for any U. from V, and this is 1 is identity element of F. Scalar 1. Scalar 1 times any element of V must be itself. So that it's called scalar identity axiom. So we have another 5 axioms. So altogether, vector space has 10 axioms. 2 axioms, closure axioms, and 8. They are properties of operations and interrelation between the operations. Okay, so now examples of vector space. The first example is P2, the set of all polynomials of this form over real numbers. You can see the degree of polynomial is 2. A0, A1, and A2 are real numbers. Summation operation is given as follows. If you take P as a polynomial of degree 2, here also polynomial degree 2. No, in general, it may be degree 1. So this is polynomials of this form. Even the coefficients may be 0. A2 may be 0, no problem. So sometimes they say this is a polynomials of degree no more than 2. 2 or less. So if you take such two polynomials, then you can add them as follows. Px, Qx is just take coefficients, corresponding coefficients of power of x. We already done it for polynomials, how to add polynomials, we know. So this is resulting elements coefficients. This is A2 plus B2, A1 plus B1, and A0 plus B2. So scalar multiplication is given as follows. Just multiply polynomial by C means multiply each coefficient is the coefficient by that scalar C. Okay, then let us consider another example. C minus infinity plus infinity. By this, we denote the set of all real-valued continuous functions defined on an entire line, real line. Addition operation is given point-wise. Multiplication operation is given also this way. So C times F is C times the value of that function F at point X. Once you consider the value of F at some fixed point F, real number. So this is the real number, this real number. We can multiply real numbers. This is the real number multiplication. This multiplication will define. It is multiplication, scalar multiplication in CR or C minus infinity plus infinity. This will define on C minus infinity plus infinity. This is operation there. But this is addition of real numbers. That addition operation in C we define by using addition in real numbers and the multiplication. Say for these functions, we can just take for each of them a real number x, one real number, another real number, sin x a real number, and the e to the x also a real number. Add up this real number, result will be the value of function, which is the sum of these two functions. Okay. All right. So here some notations which are used in linear algebra, R set of real numbers, R squared is set of ordered pairs, R cubed set of ordered triples, Rn is set of n tuples. This is a continuous function. This is continuous function. Closed interval AB. Set of all polynomials. You see, P is set of all polynomials. This is a Pn means set of polynomials degree no more than n, which n is two cases we have just now. So that this is set of all matrices n by n, m by n matrices, m rows and n columns matrices. Here just quadratic matrices. That is notations. Okay, now which kind of properties we can see in vector space? The first property is if you take zero number, zero scalar, and multiply by any vector v, you will get zero. By the way, elements of v we will call vectors. Elements of f we will call numbers, or sometimes called scalars. Zero scalar multiplying by any vector v will get zero vector. You see difference, this zero and this zero different, because this is zero of v with respect to addition operation, which is defined there. This is a zero number or zero scalar. If f is real numbers, set of real numbers, then it's just real zero. Or complex numbers, it's just zero. Or maybe rational numbers, again it is zero. So this is a number, this is a vector. Multiplying them, you will get zero. Can be easily seen. How to get it. So you will get zero number, adding zero number, result is zero number. This you write as follows: zero number times vector v is 0 plus 0, which is 0 we know, times v. Now by using distributivity, we can distribute it as 0 times v plus 0 times v. But this can, because that this is element of v, it is how to call, that is a Abelian group. So that 0 where I can add up 0 here. Let me write bold 0. This is 0 vector. So 0 vector plus some vector equals 0 times v plus 0 times v. But cancellation law gives you just cancel these two. Just adding both sides to inverse of 0 v, you will get 0 is 0v. This is the first one. Second one, exactly the same. You will take c times o equals c times o. You can write, because this is identity plus identity in v. This one is addition in v. Additive in identity plus additive identity times c equals, now if you use now distributivity, you have c times o plus c times o. Okay, but again you can add here 0. Again you can use cancellation law, cancel this two. So result, you will get this. If c times v is 0, then at least one of them must be 0. One of them must be 0. So in to find the inverse of v, you can multiply v by minus 1 because you have in your f, because being a field, it contains multiplicative identity 1. So if you take the inverse, additive inverse of that multiplicative identity, it is denoted as a minus 1. So it also belongs f. So to find the inverse of any v, you can take this inverse of additive inverse of multiplicative identity, multiply 2v, so result you will get this. Now it is easy again. Why? Because the inverse, any inverse is unique. So you have v plus minus v is 0, and you have v plus minus 1v. You can see it also is 0. Why? Because it can be written as a 1 times v axiom 10. So that by using distributivity you have 1 plus minus 1 times v. But this guy is 0, number 0, or field elements 0. So you will get 0 times v. But 0 times v is given here. 0 times v is 0. So that's why this also is 0. So that means for v, we add some element minus v, result is 0. To that v, we can add minus 1 times v also, result is 0. That means this is the inverse of v. This also is the inverse of v. So that means they must be equal. That is the proof of this. The same here. You can, what can you do is, you can do is just multiply. If c is not 0, you can multiply it by c minus 1. So in that case, just c v is 0. C is an element of, let me write it bold 0. C is an element of field. Since it is non-zero, if suppose that C is not 0, then it has the inverse, C minus 1. Just we can multiply this by C minus 1. Once you do it, then you will get C minus 1 times C times V. One side. Then on another side, you have C minus 1 times V, or 0, sorry. But according to this, any scalar times 0 is 0. So this part is 0. This part is 0. This is 1. So you will get 1 times V, which is V itself. So that means if C times V is 0, then either C0 or V0. If we suppose C is not 0, you will get V0. So that's why must be one of them. Each of these two. So C0 or V0. So that is problem number 3. Okay. Next one. Let me go to next slide. Sorry. Again. Next one, examples. And subspaces. Vector space examples and the subspaces. It is hard again. Yeah, there is a problem. Okay, so subspace. A non-empty subset W of a vector space V is called subspace of V if with vector space under the operations. Addition and multiplication given in V. It is the same. We have two operations, addition and multiplication by scalar. The two functions. We consider restriction of them. I have F from V into V cross V into V. This has subspace or subset, sorry. W, subset W, and W again here. Now we have F restricted to W cross W. So you will get the image of this must be in V. Then another one is again G, F cross V into V. Again you have here subset W cross F. The result of this must be in W again. This is the G restricted to F cross W. If you just delete this part with respect to this function, W must be an additive commutative group. Then with respect to this function must be another 5 axioms must hold. Then W is called subspace of vector space V. So here is given short form how to check for W to be subspace. In fact, if you have image in W here and the image in under this function in W enough, So that means restricting F to W times W must be in W. Restricting G to F cross W must be in W again. Image of these two functions, if they are in W, then W is a subspace. It is subspace because that other axioms interrelation between these two operations already they automatically hold. Why? Because for any element of W, you will get element of V. So that's why they are inside or already inside of V. So that's why that axioms will be held for elements of W also. Okay, so here some space and there are subspace. W5 be vector space of all functions defined on 0, 1. W1, W2, W3, and W4 be defined as follows: set of all polynomial functions on this interval. Just restrict polynomials on 0, 1. Then set of all differentiable functions 0, 1. Set of all functions, continuous functions on 0, 1, and a set of all integrable functions on 0, 1. Then easy to see, you have this. Any polynomial is differentiable, then it is continuous and it is integrable. Any differentiable function is continuous, any continuous function is on this closed interval is integrable. Then all of them are functions on this closed interval 0, 1. Here is a picture expressing that inclusions. All polynomials, then it contains all differentiable function, then continuous function, then integrable function, and all functions defined on the closed interval 0, 1. Here you can define intersection of any subspace. Then it is subspace again, can be easily seen from that axioms which already done. Okay, now span. Maybe I start from this span next time, because time is over, unfortunately. Any questions, please? You may ask. If any questions so far.
No questions. Assalamualaikum.
Rahmat, Haidarika. Well, so attendance, just please scan. Attendance. So thank you very much for your joining today's class. Unfortunately,